Good morning, everyone. So today I'm here to talk about voltage current relationship of passive elements and Kirchhoff's laws. So first, I'm going to talk on VI relationship of passive elements. That means voltage current relationship of passive elements. Passive elements means, as I already discussed about previous class about passive elements. Passive elements means resistance, inductance, and capacitance. So about the three elements, we are going to see about this VA relationship, that is voltage current relationship. First about resistor. In case of first, what is meant by a resistor? So the element which have the property, which possess the property of resistance, is called resistor. So here on the left side, you see whatever that is a physical appearance of the resistor. There are three resistances shown here, three resistors with different values here. Then these are passive elements, as we already know, and the symbol of this resistor is shown here. Actually, this is there are two symbols shown. One is according to Europe, and the other one is according to US. So that is a generally used one according to US. That is a resistance symbol. So this is a resistance of a symbol which has the two terminals. So the above one is a Europe according to Europe standard. So how is this resistance is defined? Basically, this resistance is denoted with letter capital R, and it is defined as the physical property of an element that opposes the flow of current. So definition of resistance is, it is a physical property of the element which opposes the flow of current. Now the units of resistance are ohms. So the units of resistance are ohms, and this is a symbol. This is a symbol for ohms. And again, then see here, we are going to see the voltage current relationship after the definition, and then its power and energy equation. So as we already know, resistance means it is a property of the material to opposes the flow of current, and know that at the same time, in doing so, it converts the electrical energy into heat energy. So whenever resistance is connected in a circuit, so its a basic property is it opposes the flow of current through it, and what it does is it converts that electrical energy into heat energy. So that means whenever it is connected in a circuit, when supply is given, there is a heat produced around the resistance. So that is the meaning. Then see that the voltage current relation. So it is given as like this, and resistance is a proportionality constant in Ohm's law. So in my previous class, I have explained about the Ohm's law. So there we have already came across this resistance. So this resistance is a proportionality constant, and it is given by V equal to, from Ohm's law, V equal to R into I. So from here it is written as like this. So I is equal to V by R, and this V by 1 by R, and this 1 by R is called, that means reciprocal of the resistance is called conductance, that is denoted with G, letter G. Now the units of resistance is ohm, and then the units of this conductance, the units of this conductance is mho. It is just writing in opposite way of ohm, mho. Symbol also, it is a reversal of the symbol ohm. Okay, it is also mentioned as mho, other way it is also mentioned as Siemens. So these are the units of resistance and conductance. Then power. What is the power? What is the power equation in with respect to a resistance? So using Ohm's law, the power dissipated in a resistor can be expressed in terms of R as below. So the power. So we know that from the definition of power, it is defined as rate of work done. And also we know that yesterday in my previous class, I have given this. It is also defined as power product of the voltage and current. Voltage and current. And here if we substitute in place of V, I into R by Ohm's law, from Ohm's law, then it becomes the other expression for power, it becomes I square R. Okay. Then if I substitute for I in the same expression, V into, in place of I, if I substitute for I from Ohm's law, okay, that means V by R, V into V by R. So it becomes V square by R. So this is the expression for power in resistor, okay, in case of resistor. Now, here a resistor, a linear resistor, we know that resistor is a linear element. A resistor is said to be short circuit if R equal to 0. If resistance value is 0 in a circuit, then what we say is this is short circuit, okay, and it is open circuit if R equal to infinity. That means let us say there is a supply and this is a resistance, okay. Then if R is equal to 0, R is equal to 0, okay, that means if it is infinite value, if it is there, okay, if it is infinity, this R value is infinity, what they are telling, what that means its property is, if R is equal to infinity means R value infinity means it is open circuit, it is open circuit, okay. And other way, vice versa, if its value is 0, then there is a short circuit. So R value infinity means there is open circuit and no current, okay, no current flows in the circuit. So that means current and resistance are inversely proportional to each other. Then energy. What is the energy equation in case of resistor? The energy definition, we know that it is given by energy or work done. It is given by product of power and time, right? Product of power and time. So here it is given energy from time 0 to t, okay, within a time interval it is given as from 0 to t, it is given as integral, okay. So just take an integral of p into dt. So here substitute for p, okay, substitute for p, we know that what is the power expression, okay, it may be simply vi or I square r, v square by r. So substituted here I square r, so I square r into integral of dt means it's t, okay. So we have taken what are the limits, 0 to t, so it becomes I square rt. This is a energy, okay, energy expression with respect to resistor, okay. If you consider power expression in terms of v square by r, then it becomes the energy expression is v square by r into t. Now, where V is in volts, I is in amperes, and resistance R is in ohms, and energy W is in joules, or we know that, okay. Energy units are watt hours, okay. Other units are joules. Okay, small problems, two problems are given here based on the resistor based on resistor energy power equation. First problem, a 10 ohm resistor is connected across a 12 volts battery. How much current flows through the resistor? So resistor value 10 ohm given, and resistor value 10 ohm given, and voltage of 12 volts given. Then they asked to calculate current flowing through that resistor. So from Ohm's law, simply we know that V is equal to IR. So current is given by, from that current is given by I equal to V by R. So 12 volts by 10, it gives 1.2. So 1.2 amperes. This is amperes. So that is the first one. Next, second one, a 100 ohm resistance is directly switched on across a 10 volts battery. What is the current flowing through the resistor? How much power loss? And also find energy consumed in 50 seconds. There are three parts, three things they are asking. So first thing is they asked to calculate current, okay, given resistance value and connected battery value, supply value. So I equal to V by R, 10 by 100, that becomes 0.1. Current is 0.1 ampere. And how much power loss? We know that in case of a resistor, the power expression is either simply VA or I square or V square, where anyone you can take based on the available data. So here all values we know, voltage known, current known, resistor value also known. So here shown I square R, I is 0.1 whole square into 100. So it value becomes 1 watt. You can get the same answer if you take V square by R also. So that is also shown here. Next, last line, energy consumed. Energy is given by I square RT. Okay. You can do with V square by RT also. The answer, both ways, the answer will be same. So I square, I 0.1. So here substitution 0.1 square into R into 50. So it becomes, yes. So 0.1 square into 100 gets cancelled. So it becomes 50 watt seconds. Means 50 joules. So next about element inductor. But see that this inductor, basically second element inductor, you on left side you can see the inductor. Okay, so this is how physically an inductor looks like. Because okay, see, first know what is meant by inductor, then you will understand its physical appearance. An inductor is a two-terminal element consisting of winding of N turns capable of storing energy in the form of magnetic field. So it is a winding basically, okay, having number of turns. Okay, it is a two-terminal element having winding of N turns. Okay, which is able to store energy in the form of magnetic field. So now look at the physical appearance. So you can see here a coil is shown with number of turns. Okay, so based on its capacity, it may look like this. Okay, and it's a small capacity. It is a small appearance like a thin wire. Okay, so now element is passive element. Its working principle is electromagnetic induction. So I will explain now. And then it is given by this element is given by scientist named Michael Faraday, and its electronic symbol is shown like this. See here, it is a electronic symbol. So it is a two-terminal device, two-terminal element having number of turns. That's why its symbol is shown like this. Okay, now see that here right side, look at the right side, second point, inductance is denoted with L. Okay, an element inductor have the property of inductance, okay, which is denoted with the letter capital L. And it is mentioned, it is defined as like this. Okay, it is a measure of ability of the device to store energy in the form of a magnetic field. It is ability of device to store energy, in magnetic field. And the units, it is measured in, here it is measured in henries. Okay, henries, and letter is H. Now see that, actually we know that inductance, actually it is defined as, it is ability of a device which is able to store energy in magnetic field. But basically exactly it is defined as like this. See this, look at the first two lines. Inductance is defined as, it is a property of the material which opposes any change in magnitude and direction of current passing through it. Okay, that is a actual definition. It is a property of the material which opposes any change in magnitude and direction of current flowing through it. Okay, remember, we have to remember this. Next, see that how this working principle, its working principle is explained. Okay, as I mentioned in the previous slide, it is given by a scientist named Michael Faraday. See that this is explained like this. Okay, so a change in current produces change in magnetic flux, which induces voltage across the coil. Coil means here inductor. Okay, so see that what is see that what is the point is, what he explained is a change in current. Okay, when a change in current means AC current. When a change in current produces, when AC current is connected, okay, to the coil inductor, what happens? It produces a change in magnetic field. Okay, that means change in magnetic field which opposes, which induces, okay, sorry, which induces voltage. Okay, you this is a working principle. When an AC current is applied to the coil, it produces a changing magnetic flux which induces voltage in it. That is a electromagnetic induction. Okay, given by person Faraday's laws of, okay, that is according to the Faraday's laws of electromagnetic induction. That is the principle, working principle. Okay, so now that mathematically write this. Okay, so that means what? Whatever the voltage induced is directly proportional to the cause, that the cause produced it, changing current. Okay, rate of changing current with respect to time. So that means V proportional to dI by dt. Whatever the voltage induced in the coil is proportional to the rate of change of current. Okay, so now the proportionality constant is taken as L, capital L. Okay, so V equal to L into dI by dt. Now, where L is a, capital L is a constant of proportionality, called, which is called inductance of the inductor. Okay, so L is a inductance. Okay, and the units of inductance is Henry, which is denoted with capital H. So this is how, here we see the physical appearance. Okay, number of turns wound on a core. Okay, this is a some material, iron material on that. Okay, this winding is there. Okay, this is the cross sectional area of that core, and this over the this is the total length of the core. Okay, now this is a electronic symbol of L is shown here. So when, suppose when a voltage is applied across this, okay, that is the meaning. Okay, what happens? Current I flows in the circuit, which produces magnetic flux, okay, which induces voltage V. Okay. Next, inductor. So that is a VI relationship in case of a inductor. Now, energy and power. What is a power equation? What is a energy equation? Now, see that the power. We know that basic power definition. Okay, V P is equal. Power definition, product of voltage and current. So in case of inductor, we know that V equal to L into di by dt. So substituted in place of that. Okay. So the power equation in case of inductor, it becomes L into I into di by dt. Okay. So here the power is absorbed by the element. So it is mentioned as power absorbed by the inductor. Now energy. What is the energy stored in inductor? Why that mentioning stored means? Okay, so it's already mentioned that inductor stores energy in the form of a magnetic field. Okay, so that's why it is mentioned as energy stored. So W equal to, we know this basic definition. So here substituted for power, already whatever the power expression we have, Li di by dt into dt gets cancelled. So taking L out, so it becomes I into di. So integral of I di means, okay, because from the basic mathematics we know that integral of x dx means x square by 2. So similar manner here, integral of I di means I square by 2. So the expression for energy stored in inductor is given by half Li square. So that is about inductor. Next is about a capacitor. See that what is meant by this capacitor. Okay, what is the definition? Then it's a VA relation, then power and energy. So a capacitor basically what it consists of. Okay, it consists of a pair of conductors, okay, separated by a dielectric, means insulator. Capacitor means, okay, it consists of pair of conductors separated by insulator. Now, here capacitor stores energy. Okay, capacitor stores energy. So, in electric field. So here it is mentioned as electric charge is stored in plates and capacitor become charged. Okay, so charge is stored in the conductor. Okay, this conductors means plates. Okay, conductor plates or electrodes. So capacitor can become charged. Now, what is this capacitance? So capacitance is the property of the element capacitor, which is defined as it is the ability of a material to store energy in the form of a separated charge or in electric field. Okay, so it is ability of a material to store charge in electric field. Okay, that is how capacitance is defined, and it is a exact definition. It is given by, it is a ratio of charge stored to voltage difference between the plates. It is the ratio of, okay, charge means Q, okay, it is Q to voltage. So that is a capacitance. Exact definition, C is equal to Q by V. So it is a ratio of charge stored on the plates to the voltage of difference between the two plates. Now, this capacitance is measured in farads, okay, and it is denoted with letter F, units. Okay, then look at this left side, the physical appearance of a capacitor. It is shown here based on the different ratings. Okay, it has two terminal. It is a two-terminal device. So for a small rated capacitor, it looks like this brown color one. Little bit bigger one, it looks like this black color. So on the other side, there are other rated capacitors also there. That is physical appearance. Now, type this is a passive element, and this is given by scientist name. Okay, invented by scientist Ewald George Owen Coase in 1745, and its symbol is So like this, two vertical plates, two vertical lines, okay, equal lines. So it is a two terminal device. Now look at the voltage current relationship here, VA relationship. So capacitance is defined as, okay, I already mentioned it is a property of material which stores energy in electric field. It stores energy in electric field. And it is also defined like this. It is also defined like this. It is a property of material. It is a property of material which opposes sudden changes in voltage. Opposes sudden changes in voltage. So actually, inductor is contradiction to this. Inductor opposes sudden changes in current. So here capacitor opposes sudden changes in voltage. So this is how a capacitance is defined. Now look exactly what a capacitor. Look at the second point. A capacitor consists of two metallic plates or separate surfaces separated by dielectric media. Yes, already mentioned this point. When plates are connected to a voltage source, the plates get charged and potential difference exists between the two plates. Okay, so when plates connected to the supply voltage source, then what happens? The plates get charged and potential difference exists between the two plates. The charge developed is proportional to the applied voltage, right? So so this is what's shown here in the picture. Two plates, okay, connected to the voltage. So what happens? They get charged and there is a potential difference. Okay, okay, now whatever the charge developed is proportional to the applied voltage. So here the proportionality constant is, what is the proportionality constant? C. So where C is the constant of proportionality and is known as capacitance of the capacitor. C is the capacitance of the capacitor. Right. So this is a symbol of capacitor. Two vertical lines, equal vertical lines. It is a two-terminal device. So now to get the relation, VA relation. So we know that the current definition, from the current definition, the current it is given by, so here current flowing through the capacitor, it is given by dq by, in terms of charge, dq by dt. So what is dq, what is charge from the previous slide? We know that q is equal to c into v, right? So here substituted for q, so it becomes c into dv by dt. So this is from this we get so we obtained whatever we want, VA relationship, voltage current relationship. And now get this dv this side. So the above equation rewrite, it becomes dv equal to 1 by c into I dt. Okay. So from this, what is the exact equation for V? 1 by C integral of I dt. So this is a voltage current relationship in case of capacitor. Yes or no? If we take integration on both sides, it is obtained by taking integration on both sides. So what happens? Integration of dV integration of 1 by C I dt. So this integration differentiation goes off. So V equal to 1 by C out constant integral of I dt. Okay. Next, power and energy. In case of capacitor, we know that from the definition of power, power is given by V into I, which is given as a substitute for I. Here substituted for I, so that becomes V. Okay, we know that I is equal to C into dV by dt. So substituted. So the power equation in case of capacitor is given by CV dV by dt. Next, energy. Expression for energy, we know that energy is here integral of pdt substitute for power from the above cv dv by dt gets cancelled, so integral of c dv, so c is a constant, get that out, integral of v dv equal to, okay, v square by 2. Okay, same, integral of x dx means x square by 2. So similarly here also integral of v dv means v square by 2. So what is the energy equation in case of capacitor? Half cv square. So with this we finish the old VA relationships. VA relationships in passive elements, voltage current relationships. So once again it is shown in a table. Okay. So in case of R, we know that directly from Ohm's law, V equal to Ri. Then I is given, from that I is written V by R. And what is the power equation? In case of resistor, V into I. Next, what is a L? What is a L? Inductor. In case of inductor, what is a relation? V equal to L dA by dt. So remember the above one Ohm's law, then it is easier to remember the other two. So in case of L, in place of R, replace L. Inductor. Okay. Then in place of I, dA by dt. Remember, inductor opposes sudden change in current. So I is written as dA by dt. So remember like that. From that current is written, current equation. Okay, then power. So if you remember the voltage current relationship, power equation is automatically remembered. Simply product of VI. So in case of V is V substitute, so you will get the power equation. Now in case of capacitor voltage current relationship, again from the first one. Okay, here Ohm's law, in place of R, it is 1 by C. Capacitor, okay, is 1 by C. In place of I, it is integral of I dt. Okay, so capacitor opposes sudden change in voltage. So when we write in case of current, it becomes integral. So remember like that. Okay, in place of R, we have 1 by C, and in case of I, it is integral of I. Okay, that is with respect to a capacitor. So from that current equation is written, then the power. So power equation, product of V and I, substitute for I. So in terms of V, we get the power equation.
Like, share and subscribe. Hit the bell icon for more updates.